Hey everybody, this video lesson is going to take us through a concept known as concentration, and specifically a concentration measurement called molarity. A concentration of a solution is one of the most important properties of a solution. It tells us how much of the solute is dissolved in a specific volume of solvent. In other words, it's a ratio of solute divided by solvent. I rewrote it down here so that it shows as a ratio of solute divided by solvent equals concentration. Now there's a couple of different ways to make something more concentrated. One obvious way is to add more solute into the same container, containing the same amount of solvent. You're adding more solute particles into the same solvent, and so the concentration increases. But what people often forget about is there's another way to make something more concentrated, and that's to take away some of the solvent. So you keep the same amount of solute particles in two different beakers, but one has less solvent than the other. Take a look at the scenario that I just drew in the lower left hand corner. Take the two different beakers. This is beaker 1 and this is beaker 2. Beaker 1 has this much volume in it, and beaker 2 has this much volume in it. Now if you put the same amount of solute in each beaker, one of these is going to be more concentrated than the other. The one with the same amount of solute and less solvent is more concentrated. So in summary, there's two ways to make something more concentrated. Either increase the solute to make more concentration or decrease the amount of solvent. Now the most important calculation for concentration is what is known as molarity. Now you'll notice the abbreviation for molarity is capital M. Molarity is defined as moles of solute divided by liters of total solution. So that includes the volume of the solute and solvent added together. Now that's an important distinction because some concentrations are measured just on volume of the solvent, but molarity is liters of total solution. The units of molarity are always moles per liter, or moles divided by liters. You will become very, very familiar with the calculation for molarity because we will use it a lot, many, many times. The formula to calculate molarity is basically three variables. You've got moles, you've got volume, and then you've got molarity. And you're going to be given two out of these three, or the means to find two out of these three, and you just solve for the missing variable. We'll do a couple of practice problems here. But all of them revolve around this formula, molarity equals moles over liters. Now the first thing I do is I find some important information like grams of KCl. That is my solute. My solution is usually aqueous, which means it's dissolved in water. So look for a volume of solution. I've got 400 milliliters. Now of these two numbers, I can stick volume in first, right here. And I want to make sure that it's in liters, so I move the decimal over 3 to the left. I've got 0.400 liters on the bottom. And now I can find moles by using the molar mass of KCl and converting from grams to moles. Remember, anytime you have grams and you want to convert to moles, you just divide by the molar mass. So I set up a quick molar mass conversion and take 85 divided by 74.55 and I get 1.14 moles. Now I can stick that on top, and now I just simply divide these two numbers and I'll get the molarity of the solution. And when I do that, I get 2.85 molar. So in summary, I want to find moles divided by liters, and I had the liters outright, so I just converted that to, I had milliliters, so I converted it to liters, and then I took the 85 grams of KCl using the molar mass in my periodic table. I could figure out how many moles of KCl there are, and I take moles divided by liters to find the molarity. Now another type of problem that you might encounter is one where you have the molarity and the volume, and in this case you're asked to find moles. As we know, molarity equals moles over volume. And this time I know the molarity is 0.25 molar, and once again I know the volume is 100 milliliters, and I move the decimal point 3 to the left, it's 0.1000. So the only thing I'm missing now is moles. And if I find moles, then I can convert to grams using the molar mass of MgNO3. So rearranging this formula to solve for moles, molarity is equal to moles times liter. Molarity times liter equals moles. And the molarity is 0.25 molar, and the liters is 0.1 liter. So multiply those together and I get moles. Now you don't need a calculator to do this, because multiplying by 0.1 is the same as dividing by 10, and that's just the same as moving the decimal point over to the left 1. And so I have this many moles, 0.025 moles. So I'm going to scroll up to give myself more room, and if I take 0.025 moles, and then I multiply by the molar mass of the substance MgNO3, which is back up here, I will get my answer in grams. 3.71 grams of MgNO3. I forgot to mention that I got this molar mass from the periodic table. I added up 1 magnesium, 2 nitrogens, and 6 oxygens to get 148.31. Multiply by the number of moles and I get grams. It's 3.71.
Now that we've reviewed molarity, I'm going to take a moment to explain to you how we make a solution using what is known as a volumetric flask. Now this video clip comes from a lab that I recorded, but it applies here because it's going to show you the steps that we use in order to make a volumetric solution. So you can see we've got our solvent, water, salt is our solute, and this glass piece right in the middle is called a volumetric flask. What you'll notice about a volumetric flask is that it only has one marking on the neck, which is exactly the volume that is listed on the outside of the glass. In this lab, I carefully measure out exactly 1.5 grams of sodium chloride because I want to make a solution that includes 1.5 grams. I want the solution's total volume to be exactly 100 milliliters, which is why I use a 100 milliliter volumetric flask. Now once I've got the amount of salt figured out, I set that off to the side, and I open up the volumetric flask and I deliver all of the solute into the bottom. Now some people might say that you could add a little bit of water first, and that's completely reasonable, but you don't want to fill it up all the way with water. You just want a little bit of water, but I like to just pour the salt in straight down to the bottom, and now I add my water on top. Now remember, the volumetric flask only has one marking, and as I zoom in on it, you can see in gray, this one marking, I'm going to point at it with an arrow because it might be a little bit difficult to see, represents exactly 100 milliliters of liquid. Next, you can see me adding water up to the bottom, right where the neck gets really narrow. And that's where I stop adding water because I don't want to go past the line. I want to go up to the line but never past it. And this is where I'm going to take a pipette and add that last little bit of liquid, and so that I can get up to the line, making sure the bottom of the meniscus touches the line but not going past. If you do happen to go past the line, you are going to have to dump out your solution and start all over again. If your liquid goes past the line, you actually have less concentration than you think you have. Now I'm going to calculate the molarity of the solution using the 1.5 grams of sodium chloride. I want to divide, as we showed previously, by the molar mass of sodium chloride to figure out how many moles of NaCl that I have in the solution. So I take 1.5 and divide by 58.44. I get a total moles of 0.0257, rounded off to 3 significant figures. Now because my volumetric flask held exactly 100 milliliters of liquid, I move the decimal point over 3 times to the left, I have 0.1 liters. Now if I take the moles and divide it by the liters, what you get is the final molarity of 0.257. Now it's a good idea, once you've figured out the molarity of your solution, or maybe you already know the molarity of the solution and you've made it, go back and label the molarity using a piece of tape, so that just in case the bottles get mixed up, maybe another group makes a solution that's a different concentration and they might look the same, but yours is labeled with the proper molarity. That's just good practice. Well, that takes care of this video lesson. Thanks for watching.